Hello friends, welcome back to the channel. Today we are going to talk about something that is transforming the way we build roads and control soil erosion, the use of polymers in soil stabilization. Traditionally, we've been using lime, cement and bitumen for soil improvement, but now polymers are emerging as a powerful alternative. They're lightweight, eco-friendly and highly effective. So let's dive in and explore how polymers work, their types, applications, advantages, and limitations. By the end, you'll have a clear picture of why this technology is becoming so popular in civil engineering. Soil stabilization is all about improving the engineering properties of soil, things like strength, durability, and resistance to water. Why do we need this? In many projects, the natural soil is weak and cannot support heavy loads. Roads, airfields, and embankments built on such soil fail prematurely. Erosion and dust are major issues, especially in dry regions. Traditionally, we've relied on cement and lime to solve these problems. But these materials have drawbacks. They're energy-intensive, increase carbon footprint, and sometimes not effective for certain soil types. That's where polymers come in. Polymers are long-chain molecules, either synthetic or natural, that can bind soil particles together. Some commonly used synthetic polymers are polyacrylamide, PAM, polyvinyl acetate, PVA, styrene butadiene rubber, SBR, and there are natural polymers too, like lignin derivatives, starch-based polymers, chitosan. These polymers act a bit like glue. They form a thin film or matrix around the soil particles, making the soil stronger and more resistant to water. How do polymers actually work in soil stabilization? There are several mechanisms. Cationic polymers interact with negatively charged clay particles. This reduces swelling and plasticity. Film-forming polymers coat soil grains, cutting down water infiltration and dust. Hydrophobic polymers make soil water resistant, protecting against erosion. Cross-linking polymers create a soil polymer matrix that increases shear strength and reduces compressibility. The result is a soil that is more stable, stronger, and longer lasting. Where can we use polymer stabilization? Road and pavement construction. Especially in rural or low-volume roads, it strengthens weak subgrades. Erosion control for slopes, embankments, and riverbanks. Dust suppression on airstrips, mining haul roads, and unpaved roads. Agriculture, preventing topsoil erosion and improving water retention. Land reclamation, where soils are too poor for conventional stabilization. In fact, in many developing regions, polymer stabilization is proving to be a cost-effective and rapid solution. Let's look at the main advantages of using polymers. Lower carbon footprint compared to cement and lime. Easy to apply, can be mixed with soil or sprayed on top. Quick curing and immediate dust suppression. Effective even in sandy and silty soils. Improved durability against wet, dry, and freeze-thaw cycles. In short, they're faster, greener, and sometimes cheaper too. Of course, polymers also come with some limitations. For very large projects, polymers can be more expensive than lime or cement. Performance depends on soil type. They may not work well in highly organic soils. Some synthetic polymers degrade under UV radiation. Environmental impact of non-biodegradable polymers is still under study. So, engineers must evaluate carefully before choosing polymers over traditional stabilizers. Here's a quick comparison. Cement. High strength, but expensive and high CO2 emissions. Lime. Good for clayey soils, but less effective for sands. Polymer. Versatile. Eco-friendly, fast, but soil and cost-dependent. So the choice really depends on the project conditions and sustainability goals. To wrap up, polymers are an innovative solution for soil stabilization. They offer strength, durability, and environmental benefits that traditional methods often lack. As civil engineers, it's our responsibility to adopt methods that are efficient and sustainable, and polymers are definitely a step in that direction. If you found this video useful, don't forget to like, share, and subscribe to the channel for more civil engineering insights. And tell me in the comments, do you see polymers replacing cement and lime in the future? Thanks for watching, and I'll see you in the next video.